Okay, I guess it's time to start. Good evening, everybody, and welcome to Cosmic Conversations. Now, this is a monthly talk series that we've been holding for a couple of years now, where we talk about things astronomical, not always science. I'm the host of this series, so normally I just get to introduce people and sit down. But since I'm the host, I don't have anyone to introduce me, so I get to introduce me. I'm Professor Angela Speck. I'm the Director of Astronomy here at Mizzou, and I'm a professor in this building. And today I'm going to talk to you about Pluto and why we don't consider it to be a planet anymore. Should you have questions along the way, feel free to interrupt me. I'd rather that this was interactive and you ask me as things go along than you wait to the end. So don't be shy, okay? Okay, so most of you will probably remember that, a couple of years ago there was a lot of controversy about Pluto and it being demoted from its planet status. And so there's a few jokes scattered in and amongst here because there were a lot of jokes around at the time. So let's start with talking about what it means to be a planet. It's impossible for me to explain to you why Pluto is not a planet if you don't know what a planet is. And this gets kind of complicated because actually the first 6 planets includes Earth. The other 5 we can see with our naked eyes, okay? You can go out tonight and see Saturn. Just look up in the sky, you can find it, okay? What that means is that we've always known about them. They weren't discovered. We didn't always know what they were, but they behave differently. They don't behave like stars. When we look at the sky, we see stars and they stay in the same positions relative to each other. But planets don't. They move across the sky compared to the background planets. So we've always known that they were something different. And we've always known about these 6. For Uranus and Neptune, their discovery is a little bit difficult. But Uranus was the first planet to actually be discovered. That is, we couldn't see it with the naked eye, really. And so it wasn't until someone came up with a telescope that we actually managed to find it. And that was discovered in the 18th century, okay? And so we knew that it behaved like the other planets, and so it got called a planet. But it wasn't until we started to discover lots and lots more planets, much more recently, that we realized that, well, we're going to have to come up with a proper definition. So, in 2006, the International Astronomical Union came up with a definition for the first time. In a little while, we'll look at what that official definition is. But basically, the definition that was voted on by astronomers across the planet excluded Pluto. Pluto no longer fit that description. And then there's this uproar about, oh, but Pluto's got to be a planet. It says so in my textbook. I'll come back to that. Okay, so we're going to talk about what it is about Pluto that makes it weird, okay? But in order to do that, we need to look at the solar system. We need to talk about what makes up the solar system, okay? So we're going to start by a brief guide around the solar system. Hopefully you're all familiar with the planets. There are 8 planets. Unfortunately, my laser pointer doesn't work, so I get to wield a big stick. Okay, so we have 4 inner planets, which are small and rocky, and we have 4 outer planets, which are large and gassy. Those are our planets. And I'll talk a little bit more about what makes them planets, what are their special qualities. So here we have them. They all orbit the sun. So I've got the sun here, and my planets are going around like this, okay? And as they go around like this, you don't have the Earth going like this, but then Mars going this way, or Venus going around like that. They're all going around in this one plane, okay? And that's what you can see in this image here. All the planets are basically in this one plane. They're not all over the place. They're all in one plane, okay? So that's one of the things that planets all have in common, and in fact, asteroids too. And that brings me to asteroids. So, some of you may not be aware, most of you probably are, that there are these things called asteroids. And where we find them in the solar system is between Mars and Jupiter. They're very small. Now you think about, I said, we can see the planets out to Saturn. Why is that? Well, Saturn and Jupiter are very large. So even though they're quite a long way from us, they reflect a lot of light. The sun's light hits them and comes back to us. But if you've got small things, they don't have enough surface area to reflect that much back. So we just don't see that much, okay? So the asteroids we cannot see with the naked eye. And in fact, we didn't discover them until the very first day of the 19th century. The very first one was discovered on the first day of the 19th century. And at this point, well, we've already discovered Uranus. In fact, Uranus was discovered by someone significantly earlier, but they couldn't find it again. It was lost for about 100 years and then discovered again. But even so, it's been discovered, and then there's these new objects being found. Ceres was found. There it is. It's a planet. It's an object. It's between Mars and Jupiter, and it's orbiting the sun. It must be a planet. And in fact, if you can find a textbook from the early 19th century, you will find that what it says is the planets will be Mercury, Venus, Earth, Mars, Ceres, Jupiter, Saturn, Uranus. We haven't found Neptune yet. Okay? So we've got a new planet. Great. Now, we continued looking and finding more. And in fact, over the next few years, there were another 3 asteroids found, and they were all classified as planets. So now we've got Mercury, Venus, Earth, Mars, Ceres, Pallas, Juno, Vesta, Jupiter. We have lots and lots of planets. And over the next 40 years, there was a whole bunch more found. And at this point, people realized, oh, well, wait a minute. There's this new class of objects. They're not really planets. They're too small. Ceres is actually very small. It's round, like a planet, but it's very small. So we don't really want to call these things planets. So we're going to come up with another term for them. And so these planets had been planets for of the order of 40, 50 years. And then suddenly they're not, and they're asteroids. Since then, we've found a whole bunch more. So, at the point where we discovered Neptune, and Neptune was discovered in this range, it was discovered in 1846. So around the time that we were discovering the asteroid belt, we also discovered Neptune. But since then, we've discovered a whole bunch more. And I want to just give you an idea of that. Before I do that, I want to show you this. This kind of gives you an idea of the scale. I want to point out 2 things. So this is Mars here. This one is Ceres, and these are a bunch of the largest of the asteroids, trying to give you an idea of scale. But the scale in distance is not the same scale as the size, okay? To put this in perspective, the distance from here to here is the distance from the Earth to the sun, okay? So all of that is actually quite spread out. I'm pointing this out because most people think of the asteroid belt as being this thing that's densely packed with these rocks that keep hitting each other, especially if you've seen Empire Strikes Back, right? There's lots of asteroids hitting each other and causing all sorts of explosions and destruction. It's nowhere near that densely packed, okay? So I just wanted to give you a feel for that. But the other thing I want to show you is, so here we have end of the 18th century. We haven't found any asteroids yet, okay? 100 years later, we found a bunch of them, okay? 50 years later, we've got quite a few. About 20 years ago, still quite a few more. And then about 10, 11 years ago, this is our known asteroids. So as our ability, we're trying to detect things that are very small, and how much light they reflect depends on what they're made of. If they're made of something that's dark, they don't reflect much light, so they're hard to spot. If they're made of something that's light-colored, they reflect a lot more light, they're easier to spot. And so as our technology has got better, and especially with things like the Hubble Space Telescope, where we don't have to worry about the light passing through the atmosphere, we see a lot more. And so this is the current state of our discovery of asteroids. All the ones colored in red are the ones that cross Earth's orbit. I'll let you figure out for yourself what that means. Okay, so this is just to give you another view on where they are. I've got the orbits of these asteroids here. So we've got this blue line is the orbit of Ceres. This one is Juno. This one is Pallas. And then you've got some of these asteroids that are coming from the asteroid belt and then going past the Earth and in towards the sun, kind of like comets do. Those are the ones that are likely to hit us. Some of them do. OK, so that's the asteroid belt. Now, so we've discovered the asteroid belt, and we've discovered Neptune. And here's another thing. Neptune was discovered in 1846, but it was actually seen by Galileo in 1612, 3 years after he first pointed a telescope at the sky. He discovered, no, that's not fair. He saw Neptune, but he didn't recognize it as a planet. It was just a star. It didn't move very far. You know, it takes a long time for Neptune to go around the sky, so he didn't recognize it as being a planet. He recognized it as being a star. So he saw it, but he didn't see it as it wasn't discovered as a planet until 1846. So now we've got most of the planets that you're familiar with and the 8 planets that we consider to be real planets. And then Pluto was discovered. And it was discovered in 1930 at the Lowell Observatory, which is just outside of Flagstaff in Arizona. Incidentally, it is a law in Arizona that Pluto is a planet. And in Flagstaff, doubly so. OK, so Clyde Tombaugh, using the telescope, pointing at the sky, finds this thing. And they called it a trans-Neptunian body. They didn't call it a planet. They called it a trans-Neptunian body. What does that mean? It's a thing out there, and it's beyond Neptune. That's all it means. OK? And that's what they called it. And it was only maybe a little while later that it was actually, you know, we're going to call this thing a planet. OK, a couple of years. It was basically making it into the textbooks that this is a planet. OK? OK, so we've got Pluto now. But I want to share this with you. And I'm going to give you time to actually read this. So I'm just going to give you a couple of minutes to read this slide. I want to draw your attention to a couple of things. Pluto has been a disappointment. Pluto ranks as the largest asteroid rather than the smallest planet. This was published in 1934, 4 years after its discovery. This is not something new. This is not something that we came up with this decade. This was something that people are already going, it's not what we expected our outer planet to be. Okay? And since then, we've had a lot of debate. It isn't that this debate's only been going on since the IAU defined a planet. This debate has been going on basically since Pluto was discovered. Okay? All right. So now I have to come back to what is the solar system. We're still doing our little tour of the solar system. So we've got our 8 planets. We've got our asteroid belt. So you've got the inner planets, which are small and rocky, the asteroid belt. Then you've got the outer planets that are large and gassy. And beyond the outer planets, there is another belt. It's kind of like the asteroid belt, except that the objects in it are icier. So the stuff that's in the asteroid belt is mostly rock. Okay? You can think of it as being small planets that got broken up during the early solar system with everything colliding into each other. As you get further and further away from the sun, ice can survive. So, you know, when you're by Earth, we have got some ice on Earth, but it's not very stable. But as you get further and further away, ice can then exist. And so now you've got bodies where there's lots and lots of ice. And this is basically what we've got here. So here I've got, this is the outer planets here. So this green ring here is Neptune's orbit. The blue ring is Pluto's orbit. And this is the location of the Kuiper belt. And what we've got here is an edge-on view. So this is the orbit of Neptune and actually just about every other planet. And here's the orbit of Pluto. I'll come back to that. And this is basically saying if you've got an object up here, it has to orbit the sun. The sun is in the middle over here. So what you've got is this thing's got to come down around like this and back up. So anything that's offset from the sun, it has to go around it. Okay? Now, the Kuiper belt was originally something that this guy, Kuiper, came up with because of comets. Okay, so we see these comets. We see comets all the time. We've seen them throughout history, through prehistory. Some of them don't ever come back, but a lot of them, they come back in time and time again, the most famous one being Halley's Comet. Okay? But there's lots of comets, and they essentially are orbiting the sun. But their orbit is like the ones that I showed you of the asteroids, where they start a long way out, they come in, they come right past the sun, and then they go back out. Their orbit is this long oval shape. It's a big elliptical shape, but it's orbiting the sun, just like the planets do. Okay? And they're made of these icy bodies. And so what Kuiper said was, you have to have a place out there beyond Neptune where these rocks come from, where these icy chunks come from. So this was a repository for comets. Okay? When Pluto was discovered, it wasn't recognized as being a Kuiper belt object. But as time has gone on, we've started to discover more and more of these things. So let's have a look at them. Oh, this is just another view of this to give you an idea of it. So remember I said that if this is the sun and the planets are going around in a plane, once you get out there, it's more like, instead of being, a nice flat disk, like a DVD or something, it's now a bit fatter, so it's more like a donut. Okay? So what you've got is, instead of being all in this one plane here where Neptune is, they can be spread out a bit. They still have to go around the sun. Okay? And this is just another view of that, which actually shows you some of the other objects' orbits. So you can see where Neptune is, and then there's this band where we're starting to see these other objects, very much like the asteroid belt. Okay. And this is basically a plot of the known Kuiper belt objects. Now remember that when we're detecting asteroids, we've got light from the sun, has to get out beyond Mars, hit an asteroid, and come back to us. For the Kuiper belt, that light has to come from the sun, go all the way out past Neptune, and then all the way back to us. So it's harder to see them, because they're not any bigger than the asteroids. Well, some of them are. But they're so much further away from the light source and from us, it's very hard to detect them. So even now, we haven't got that many that we know about. Okay. But I wanted to give you an idea of some of the ones that we do know. So here we've got, for scale, our moon. Pluto is smaller than our moon. This object, Quaoar, I'll come back to again. This was one of the first ones to be discovered, was discovered about 7, 8 years ago. And I think it's been renamed Maki. I have no idea why Quaoar wasn't good enough. Okay, then we have another one. This is just to give you an idea of the size of these things. So we've got the Earth for scale again. Here's the Earth. Here's this one, Quaoar. There's Pluto, which we now know has 3 moons. This is its biggest moon, Charon or Sharon, depending on who you talk to. Nix and Hydra. This is another one that was discovered. This one had a number for a while, was very briefly called Xena, after the warrior princess. And seriously. And it has a moon, Dysnomia. Okay? And then there are these other ones that you can see. These ones still don't have names. Even ones that don't have names have moons. Okay? And this is just to give you more idea of how many we've got. So here's Mercury and the moon. Triton is one of the moons of Neptune. Here's Pluto and its moons. This is here's Eris and Dysnomia, one of the ones that doesn't have a name. A whole bunch of other ones that some of them have names, some of them don't. Here's Texas for scale, because we all know that Texas makes a really good scale.
What is a qualification for a moon to make it? I mean, a planet to have a moon. I mean, Pluto has a moon. What's the difference between its moon and Pluto?
Okay, I will actually come back to this, but so basically a moon is something that is orbiting a planet. Okay, that is our definition of it. So our moon, technically, actually, if you've got the Earth and the moon, we're actually orbiting a point somewhere that's not quite in the center of the Earth, right? So we're kind of orbiting around to some point. But it's mostly around the Earth, right? So the moon's going around. Same with the moons of all the other planets. Actually, for Pluto, it's a little different, and I'll come back to that. So, and you can see also on here, there's the largest of the asteroids, so Ceres and Vesta and Pallas, so that you can see them for scale too. So this is just giving you an idea of how many of these we've found and what sort of sizes they are. And there's going to be a whole bunch of them that are smaller that we just can't see. Okay, so we've now got a structure for the solar system. We can go back to what makes a planet and what can qualify something as not being a planet or as some other object. So, what is it that planets actually have in common? Well, they're all in orbit around the sun, and they're all going the same way. It's not like one goes this way and then the other goes that way. They're all going the same way around. Okay? They nearly all rotate that way as well. Venus doesn't, and there are ideas about why that is, but basically, as well as going around like this, they're also spinning that way. Okay. What else do planets have in common? Well, now, I've already talked about this. We've got this idea of them being in a plane. They're not all exactly in the same plane, but it's very close to the same plane. So you can think of it as being there's this kind of disk that's not very fat that is where all the planets can be found, okay? The ecliptic is actually a way of defining where you would find them on the sky. Because when you're looking out into to planets in space, you actually define them by what stars are behind them, okay? And so we already saw this. We saw that for the planets, they're essentially all in this zone here. They might be very slightly above or below this line, but they're all basically in this plane. Pluto is not. And a lot of the other Kuiper belt objects are not either. They also, nearly all, have circular orbits. They don't have exactly circular orbits. No planet has an orbit that is exactly circular, okay? But they're very, very close to being circular. Pluto doesn't. And we can see here, you've got the sun, and you've got all of these orbits, and they're very, very close to being circular, except for this one, which is kind of a little elongated. It's more elliptical, okay? And the same is true for the Kuiper belt objects. Remember, we talked about also for a comet, you have a very elliptical orbit, okay? Because it's basically coming from somewhere out here, and its orbit is so elongated that it comes all the way in and all the way back out again. Okay, so what is different about Pluto? Well, we've already mentioned a couple of these. Pluto has this elongated orbit, which means it actually crosses. When it's at its closest point to the sun, it is closer to the sun than Neptune is. Okay? And at its furthest point, it's actually a long way out. So at its closest point, Pluto is about 30 times our distance from the sun. At its furthest point, it is 50 times. That is a big difference. Okay? And then we talked about how it's offset. So, and this is something that's important for why you will never have Pluto and Neptune actually hit each other. Because although their orbits overlap, they're not in the same plane. They're going, one's going at an angle like this, and the other one's like that. Okay? So they're not going to hit each other, ever. Okay, so that's already something that's different about Pluto. So lots of people think it's like, so what? It's a planet. It's always been a planet. It's been a planet through all my life. Okay, well, I want to put that into perspective for a start. So when I got into astronomy, I was about 5 or 6, and Jupiter had 13 moons. I still have a game that is one of these trivia games for kids that says that Jupiter has 13 moons. By the time I went to college, the Voyager mission had gone past Jupiter, and we knew about a few more, and Jupiter had 16 moons. So my textbook that I had when I was very young said it had 13 moons, but my textbook in college said it has 16 moons. Last semester, I taught an upper-level class on the solar system. How many moons do you think Jupiter has?
63.
Very good. Hey, he did his homework. You didn't do my class, did you? It has 63. Okay? Things change. Deal with it. We find new things. We update our ideas. So just because it's in a textbook doesn't mean that it's right. And remember, if you can find a textbook from the early 19th century, Ceres will be a planet. You won't find that now. Okay? Okay, so some of the reasons that people put forward for why Pluto should be a planet is that it has moons. This has already come up, and we'll come back to it in a few minutes. It has an atmosphere. This one's really good. You're going to enjoy that one. And my favorite, but we've sent a space probe to Pluto, so it must be a planet. Okay. Okay, so we can start with the moon thing. Yes, it has a moon. In fact, it has 3. So what? So does Eris. Has its moon dysnomia. So does this one that doesn't have a name. This is one where you can see. So this is time-lapse observations where you can actually see how this other object is orbiting it. This one is Ida. This little dot here is Dactyl, its moon. That one's an asteroid. It's not a Kuiper belt object. That one's in the asteroid belt. Okay? So a moon is not a sufficient way of defining a planet. We have another problem with, oh, well, it must be a planet because Mercury doesn't have a moon. Venus doesn't have a moon. So we suddenly have to demote those. Okay. And then this was something that was already mentioned. So we've got, this is just to give you an idea of what this is like. So we've got, here's Pluto, here's its moon Charon, and here's the Earth for scale. They're pretty close together. And they're actually, in terms of mass, pretty close together too. And this leads to an interesting situation where they're locked tidally. Now, some of you may be aware of this idea that when we look at the moon, we always see the same face. And it's because it's tidally locked. I need a volunteer from the audience. Okay, what I want you to do is, I want you to walk around me, but I want you to walk around me while looking at me the whole time. So you have to walk around me so that you're facing me all the time. Okay, just keep going. Keep going. Keep going. Keep going. Keep going. No, you don't have to. You can move your whole body. That's fine. Okay, so for the moon, this is what's happening. It's actually turning. You noticed he had his back to you when he was here, and his front to you when he was over here. So he's actually moving through a full orbit. It just takes one full orbit to do one rotation. Okay? That's what the moon does. Now we're going to do this again, and you don't have to twist your body. You can move your body around so you're looking at me, okay? I just want you to do the same thing, but I'm going to be Pluto now instead of the Earth. Okay, so let's do this. Excellent. You can sit down. Thank you. Okay, so whereas for the Earth and the moon is doing that, for Pluto and Charon, they're both doing it. So it's always the same side, which is kind of interesting, because what it means is that if you were to live on Pluto and you were on this side, you would never see Charon, because Charon would always be on that side, right? Because of the way it rotates. It means you would have to go to the other side of the planet just to see its moon. Okay? But the other thing is that they're not rotating around a point inside of Pluto. They are going around a point outside. Okay? So the point about which it's not that Charon goes around Pluto like this. They actually orbit around a point about here. Okay? So both of them, they're going around like this. And so actually some people have argued that you would call this a binary planet, where it's like a dual planet, rather than being a regular planet. Okay, and so we've got this interesting situation where actually its moon makes it less like a planet than other objects, not more like a planet. Okay, now another thing that we should talk about is, we know that we've got the inner planets and they're rocky, and they vary in density, but they're basically made of rock similar to the Earth. Okay, not exactly the same, but similar. And then you've got the outer planets, and they're basically made of gassy stuff, mostly hydrogen. As you get further out, maybe some methane. Pluto isn't like either of those. Pluto is very, very small compared to any of the other planets, and its density is incredibly low. But it's a solid. So it's, the density of the gassy planets is low because it's a gas. Of course the density is low. The density of the rocky planets is what you would expect of rock. Pluto's kind of in between, and it lets us have a guess at what it's made of. And it is made of a significant fraction of ice. And this is kind of like what we have for comets. This is what comets are made of. And remember, comets are coming from the Kuiper belt, which is where Pluto is. It's looking more and more like it's a Kuiper belt object. Okay, so let's now get to the really fun one. Pluto has an atmosphere, but not all the time. Pluto's atmosphere is only there for a short time at perihelion. What do I mean by that? When it's closest to the sun. So we saw how its orbit, at one point it's very close, it's closer than Neptune, and at the other end of its orbit it's much further away. Okay, when it's in that very close in part of its orbit, it has an atmosphere. When it gets further away, the atmosphere disappears. And this is just to try and show you what I mean by this. Okay, so we've got it, when it's its closest point, it has an atmosphere. And what's happening is, remember, it's getting closer to the sun. It's 40% closer to the sun at perihelion than at aphelion. At its closest point compared to its furthest point, it is 40% closer. So obviously it's hotter, because it's closer to the sun. It's so hot that it actually makes the ice evaporate. Okay? The ice is there, it evaporates. So now you've got gas around the planet. It doesn't all just drift off into space right away, but it's just going to, it can't hold on to it. The mass of the planet is too low. It doesn't have enough gravity to hold on to that gas, so that gas is going to drift off into space. But it takes a while. So for a short time, it has this atmosphere, but then as it moves away, it's no longer warm enough to do that. The ice is just ice. It can't evaporate anymore, so it's no longer got that atmosphere. Well, this is kind of interesting, because when we look at comets, this is what comets do. A comet is typically a chunk of ice that's 10 kilometers across. It's come from the Kuiper belt. And as it gets closer to the sun, it starts to evaporate that ice and build up this big atmosphere. And most of what we see in a comet is this enormous amount of evaporated ice. The ice is evaporated into gas, and we can see that. It's reflecting sunlight, and we can see it. Okay? And it goes around the sun, and it comes back, and it goes back out. And when it gets back out, past about Jupiter, we can't see it anymore, because it stops making that big atmosphere that it has. For a comet, we call it a coma, but it's an atmosphere. It's just a transient one. So Pluto is actually behaving like a comet. It's coming from where comets come from. It's crossing the orbit of a planet, and it is developing an atmosphere at its closest point to the sun. It's behaving like a comet. Okay? Okay, now the silly one, space probes. So there's this argument that, well, we wouldn't send space probes to something that wasn't a planet. First of all, the people who are arguing this are mostly planetary scientists and are being very short-sighted about how to get things out of NASA. But it's also not true. So we have this probe, and it was launched. It's on its way. But in fact, the New Horizons probe was never intended to be just a probe for Pluto. The whole point was to investigate the Pluto-Charon system and the other objects out there, the Kuiper belt objects. So it was never intended to be just a probe to Pluto. But the other thing is, we've sent lots of missions out there to comets. Stardust was a mission from a few years ago. I think it was 2002, 2003, where they sent a probe through the tail of a comet to collect the stuff that was being evaporated off. And they brought it back, and it crash landed in Utah so that we could have those samples. Deep Impact was one where we crashed it into a comet to see what came off. So we crashed this thing into a comet, and then we point telescopes at it and see what comes off. And in fact, Deep Impact 2 is going to happen late this year. Okay? Rosetta was a still in progress probe to actually land on a comet, on that small body that's evaporating, and do sample analysis in situ. So you land this thing, just like the rovers were on Mars are analyzing what the rocks are, it's going to do the same thing on a comet. And Giotto was one of the first ones to go to a comet. It went to Halley's Comet. The last time Halley's Comet came around was 1986. And I guess there's only a handful of people in the room old enough to remember that. I might just about last to the next go-around. Okay, so, you know, invoking the space probe is a really silly argument for why it should be a planet. Okay, so we've talked about why Pluto is different from planets, and in fact, we've even proposed a new definition for it. But we haven't actually talked about what the definition is, the official definition of a planet, as defined by the International Astronomical Union. This is the actual document, and I'm going to zoom in on the relevant part, okay? This is the actual document that people who went to this general meeting saw and voted on, okay? The important bit is this. It says, a planet is a celestial body that A, is in orbit around the sun, B, has sufficient mass for its self-gravity to overcome rigid body forces so that it assumes a hydrostatic equilibrium. Means it's round. C, it has cleared the neighborhood around its orbit. Okay, so things that orbit the sun. Well, nearly everything in the solar system orbits the sun. That doesn't narrow things down much. Sufficient mass for its self-gravity to overcome rigid body forces. Means it's round. You remember when we looked at the asteroids, most of them weren't round. Ceres was. Ceres would still fulfill this requirement. Okay, so Ceres would be a planet. Pluto would be a planet. Quaoar. Actually, let me back up and just talk about Quaoar for a minute. So we talked about Pluto and how its orbit is elongated and it comes in close to the sun and goes further out, and it's not in the same plane as the planets. Quaoar, or Maki, it's a little further out than Pluto. It's a little smaller than Pluto. But it's almost certainly round. Hard to tell. It's far enough away, it's kind of difficult to actually get that for sure. Almost certainly round. It has a circular orbit and is in the plane of the planets. It is more planet-like than Pluto is. So there's another one we're going to have to include if we start using those definitions. But the one here that really does Pluto in is cleared its neighborhood. So remember, we've got just like with the asteroids, you know, you've got Ceres, and then you've got all these other rocky bodies, and they're all overlapping in their orbits. That's what's happening out in the Kuiper belt. Pluto is there, and it's going around, but so are all these other things, and they're all overlapping. And so it doesn't do that. Now, this gets a little bit complicated because people argue that, well, comets come past everything, so nothing's cleared its orbit. But they're rare, whereas the objects that are in the same orbit as Pluto, they're overlapping a lot, okay? And so it's a slightly different situation. So within this, there was also the proposition to define a dwarf planet, where basically it is the same definition, but it has not cleared the orbit. And this time they've decided to say it's not a satellite, because we've got lots and lots of round moons that orbit along with our planets around the sun. They'd have to be planets too. So now we're getting satellites thrown out as well. So we've got this definition of a dwarf planet. And this is basically where Pluto falls. But I think this does a disservice to Pluto. You know, Pluto is this object that it was the very first Kuiper belt object ever to be discovered. It is the biggest comet we have ever seen. It is way more fun than just a dwarf planet. Maybe we can call Ceres a dwarf planet. That I'll accept. But Pluto is something that's much more interesting in terms of understanding all sorts of things about how the solar system works, how comets work, and all sorts of stuff like that. So I'm not going to talk about that. Okay, so we've got all these reasons why Pluto is different. Now, I don't know how many, most of you probably weren't here when Neil Tyson came and gave a talk on campus. I think that was 2003. How many of you know who Neil Tyson is? Okay. Neil Tyson is one of the most famous astronomers on the planet. He's frequently on the Colbert Report and The Daily Show, black guy, runs the planetarium in New York.
I have a picture of me with him on my side.
Very good. He's very cool. He did actually come here in 2003 and gave a talk on Pluto. He's actually had not quite death threats, but hate mail for removing Pluto from the planets in the planetarium in New York. He's actually written a whole book that contains some of these things. You know, and he's done a lot of stuff, and we're very passionate about it. Like I say, in Arizona, you've got this law that says Pluto is a planet, because that's where it was discovered. And there's also this idea that, particularly in the US, that there's this affection for it because it was discovered in the US. You know, like I say, we've only discovered a handful of objects. In fact, we've only discovered 2 planets under the current definition. We discovered Uranus, which was discovered by William Herschel, and almost called George, after George III. I'm sure that would have made Americans really happy. And Neptune, okay? Which was discovered by now, was it a Frenchman or a German? They were fighting it out. And then you've got Pluto, discovered by an American. So, you know, in this country, there's even more passion for this thing. But it's silly. It's, you know, we can have it as something that's much, much cooler. So I'm going to just summarize what we've gone through. So it does not orbit in the ecliptic plane. Remember I said this is the plane that all the planets are in? It's not in that plane. So that's strike one. It has a highly eccentric orbit. That is, its orbit is not circular. It is very elliptical. It only has an atmosphere when it's at its closest point to the sun. It has not cleared out its path. It shares its orbit with a lot of other objects. It does have a moon, but we can't use that as a criterion for defining planethood. And basically, we have a precedent. Now that we found more of these objects, we have a precedent for this. Ceres was a planet. Then we realized, no, there's lots of things there. It's an asteroid. Pluto was a planet. Oh, wait, there's lots of these things out there. It's a Kuiper belt object. But because of how it behaves, I would argue that actually we should call it a comet.
So I noticed that you talked about the atmosphere, but it wasn't in the definition of the plane.
No. No, but this is the thing. Neither is the inclination angle of the orbit. There are lots of things about Pluto that are much weirder than the definition is actually, you know, doesn't tell you the full story of why Pluto is this odd thing that we shouldn't. I mean, it throws Pluto out of the planets, but it doesn't give you the full story.
How is Pluto different than the other large objects in the Kuiper belt? Because, like, since it's not, you said it should be a dwarf planet and a comet.
Okay, so I'll leave this up for now. So some of them are like it, some of them are not. So we said Quaoar is in the plane of the planets and circular. So it doesn't do the, I've got an atmosphere at one end of my orbit or the other. There are others that are at that point. We haven't managed to watch them for long enough. Remember, it takes, I forget what the exact length of the orbit, it's about 250 years. So Pluto hasn't had time to do a full orbit yet. So there are some of those objects that we expect to do the same thing, but we haven't observed them do it yet because we haven't seen them for long enough for them to come in close. But based on, we can see from their path where they're going to go. Based on where they're going to go, they're going to be like Pluto. It's not unique. But I think calling it a comet is, well, you could call it a comet or a dwarf planet. But I think comet does it more justice given how weird it is. And I'm going to stop there. And you can ask me any questions you like. No more questions? Flummoxed you all?
Well, you mentioned the atmosphere that appears when it's at perihelion. And you stated, perhaps for simplicity's sake, that the atmosphere disappears, it goes on. Is that really the flow of the economy, or is it largely recaptured, refrozen?
Well, you'll have a little bit of both. So when you've got an atmosphere, whether you can hold on to the atmosphere depends on temperature and mass. So you'll have some of it will be evaporated and it will escape. As it's getting to the point where it's no longer evaporating, that's the point at which the stuff that's high enough up will escape, and the stuff that's not will actually, it's getting colder, it's not going fast enough. Temperature is just a measure of how fast the atoms in the room are moving. And so as it gets colder, they're moving slower, and they tend not to get as high off the ground. And eventually, they're just going to fall right back down. So you have both things going on. And in fact, for comets, it's an issue. And this is why the Kuiper belt was invented, because you've got these objects that are 10 kilometers across. They're coming in really close to the sun, and this stuff is going off into space, and you can see the tail of it drifting off. They can only do about 100 or 1,000 orbits. Well, that's a lot less than the age of the solar system. So you have to keep having more. So what you've got is, you've got this repository out there of these blocks that can get gravitationally pulled out, and then they'll go into an orbit like a comet. And that's actually why the Kuiper belt was hypothesized in the first place, was to have a place that comets could come from. There was another question back here. Okay.
So how likely do you think it is that we would have a change in the number of planets again?
The number of planets, I don't think we're going to change. I mean, there's a lot of people going on about how we have to, put Pluto back into the planets. And if that happens, then we have to have shed loads of planets. And that was a shed, by the way. But I think that most astronomers, even those that live in Arizona, are pretty happy with this state. So we're going to add more dwarf planets. I have no doubt about that. And we're going to add more Kuiper belt objects as we can see smaller and smaller things. But I don't think we're going to add any more planets within our solar system, because we now have over 400 planets around other systems. And that causes all sorts of issues with definitions of planets. But we do call those exoplanets, so they're different. So there's another question.
So I read somewhere that Pluto's color was changing, like it was becoming more red.
Sorry, say that again?
That Pluto's color was changing, that was becoming more red. Does that have anything to do with the atmosphere and how it goes away?
It's becoming more red.
I read that on NASA.
Yeah, you see, as an astronomer, I take becoming more red in a slightly different way. Color will change, and we see this actually with asteroids, that asteroids get resurfaced. And what happens is that if you can think of it as being like, I don't know, how many of you have been to Hawaii? Not many. How many of you have seen pictures of Hawaii? There we go. Okay, depending on where you go in Hawaii, you either have this brand new rock that's black, or you have the rocks that have already oxidized and are red, okay? Anywhere that you have an atmosphere, anywhere that you have any sort of active surface, you get changes in color because it's just to do with what's there. We see it for Europa, which is an ice-covered moon of Jupiter. We see it for asteroids where they're actually made of like a pile of rubble, and they don't even have to hit another one. They just have to come close enough to something for gravity to kind of pull on them. And because they're like a pile of rubble, you disrupt one little grain, and they all slide into a new configuration. But then you've uncovered stuff that hasn't been hit by solar wind, and so it has a different surface. And so we see changing colors all the time. As an astronomer, I regard becoming red as getting colder. And so Pluto is getting colder because it's on its way away from the sun. So it's also possible that that was the intent of the word. But it is, we see the surface changing.
What's like a proposed hypothesis for the creation of the Kuiper belt?
Okay, so that's a whole talk in itself. Let me do the simple version. Okay, the idea is that the solar system formed out of a cloud that collapsed. So you've got this enormous cloud of stuff. It's gas and dust, and it collapses in towards the center. But it's also spinning. And because it's spinning, it will tend to form a disk, okay? Now, the reason for that is, how many of you have ever seen someone who is making a pizza properly, where they have a bowl of dough and they throw it in the air and it spins out? Okay, that's basically a normal force that happens. Something spinning, it will tend to make it spread out away from the axis of rotation. And so what you have is this thing is falling down, but it's also spinning, so it will tend to fall down okay perpendicular to the axis, but, parallel to the axis, but spread out. So now you've got this disk. And basically, it's there because you have lots and lots of stuff that forms in that collapse. It's far enough away that you get ice, so it's not very hot, but it's not dense enough to actually have coalesced into a planet. And that's kind of what happened in the asteroid belt, only there you have gravitational forces due to Jupiter.
So the ice was already a part of those objects?
Well, what you get is not all of it. So it's already made of gas and dust. Not all of it will evaporate, but most of it will become gas. But then it will start to cool down. And as it cools down, you form different things. And so you'll form all of the... This is actually how you explain why you have rocky planets close to the sun, gassy planets further away. And it's basically, you need to think of it in terms of hydrogen is really, really abundant. Oxygen's fairly abundant, so is carbon. So it's really easy to make water, carbon dioxide, and methane. And so there's lots of that stuff to play with. And that's where it's actually cold enough to be ice. Other questions? Okay, I'm done.